Okay, chapter 9 of Pearson, basic chemistry. We will do the lecture, and we'll do a work session as well to go through the details of all of these. In this chapter, you'll look at conservation of mass, calculation of mole using mole factors, and this is no sweat for you. You now know you put it in the dimensional analysis machine, and you punch it through until you get an answer at the end. Mass calculations of reactions, you can do that. Limiting reactants, you can do this because you know how to put it in the machine. At the end, you're going to read the output. You're going to put it in the app, and you're going to read the output. All of these use the same app, okay? You just have to read it at the end. Energy and chemical reactions, they work the same way too. They all get plugged into the app. So let's look at it. The law of conservation of mass indicates that in an ordinary chemical reaction, matter cannot be created or destroyed. No. Okay? You can't destroy nor create matter. That's it. Okay? The mass does not change. If we start on the left side with reactants and we have 10 pounds, we have to have 10 pounds on the right side. Now, what was wrong with the statement I just made when I said 10 pounds on the right and 10 pounds on the outside if I'm in a scientific laboratory? It's not the scientific term. You got it. Very good. Okay? You get it? What terms would I use in the laboratory? Grams or kilos. You get it? Very good. If I'm in a plant, on the other hand, I might use pounds. You got it? So be aware of that. Very good. Okay, so no change in total mass. Mass of product equal to the mass of the reactants. That's it. Be aware of that. The combustion of methane. So here we have the combustion of methane. Is this equation balanced? Indeed it is. Is this complete combustion or partial combustion? I'm sorry? Partial or complete? Here's your key. Complete. If CO2 comes out, it's complete combustion. If carbon monoxide comes out, it's incomplete combustion. Okay? So here, the combustion of methane with oxygen, you can calculate the mass. So here, if we want to calculate the mass here, I think we do it. If we want to calculate the mass here, we simply add up the molar mass, methane, the molar mass of oxygen. If you add this plus this, and you calculate the molar mass of carbon dioxide and these, you'll find the molar mass on this side when they're summed times the coefficients, okay, because it's a reaction. Now that's not the molar mass, that's the molar mass times the coefficient. The coefficient, make a note of this because someone's going to make this mistake because we're switching this thing. When calculating the molar mass, do not use the coefficients in front of it. You only use these when you're trying to determine what happened in the reaction. The molar mass is simply the molar mass universal around regardless of what the coefficients are, regardless of how it's used. The molar mass of methane is what it is. Molar mass of oxygen is what it is. Regardless of how many coefficients you put in front, do not use them in calculating the molar mass. However, when you have to calculate the total mass of a reaction, then you use them. You want to know, what was the total mass of this reaction? If you're in the plant, how many pounds should I put in this kettle? If you're in the laboratory, how many grams or kilos should I put in the flask? You get it? Okay? So be aware of that. And pounds only work in the U.S. too, right? If you're in Europe, then how many kilos you're going to put in the plant? Okay. So there we have it. So this side must balance with this side in terms of the atom count, the electrons, and the mass. You get it? The atom count, the electrons, and the mass. They all have to balance out. Now, when you bake a cake, you blow out CO2, but you don't collect it. It kind of goes into the house. But you get out the cake, you have just the cake left there, and this mass is going to be left because you blew the CO2 out. So here we have the solution to it. We take what? 1 mole of methane plus what? 2 moles of oxygen. Okay? Methane mass is 16. Oxygen is 32 times 2. Does everyone see where we get the 64 grams here? Okay? This is 32 times 2. And we add it up, we get the mass, total mass on this side is 80. Do the same thing over here. 1 mole of carbon dioxide is 44.01. Water is 18 times 2 gives us 36 grams of water out of this reaction. And so the mass on this side equals the mass on that side. You got a problem like that in chapter 7. Someone sent me an email asking about that one, I think. Okay? I don't remember who it was. So this is how we do it. And this is how we know it's balanced. The equation this is why the equation must be balanced. This is why the atom count has to be balanced. That you see how to get the mass balance. Okay? Questions or comments? Are we okay at this pace? All right. Let's look at mole factors in a balanced equation. If you have a balanced equation, this is a legal scientific equation. It can be used for conversion factors. But do we use the conversion factors to determine our sig figs? No. Because a balanced equation is a balanced equation the world around. Okay? It is a universal standard. We don't use it. But what we note here is, and we've been through this in other sessions, we've introduced the concept. When the equation is balanced, that tells me I have 2 irons to every 3 sulfurs. I have 2 irons to every 1. Does everyone see that? Of this species. Right? Of iron 3 sulfide. Okay? I have 3 sulfurs to 1. Does everyone see why? We look at the species, and we simply look at the coefficients, and so any of these ratios you use as needed. You will not have to memorize these if you use the app, if you use the dimension analysis machine. You'll simply look at the balanced equation, and you'll plug them in there. Okay? You balance the equation, run the app, plug in the values. Balance the equation, run the app, plug in the values. Over and over again. Okay? Sounds too strange, but if you trust me on that, you'll do well on these. Here we have one. In the chemical reaction of iron and sulfur, how many moles of sulfur are needed to react with 1.42 moles of iron? Well, we're going to do this one. I'm not going to even show you here. I'm going to pause this, and we're going to work this one on the board first. Yes. So there we have iron plus sulfur. Here's the solution. You know, the author here likes to write out every ratio in the world. You don't have to write out all these ratios all over your paper and see if this is over that. I'm never going to ask you all these ratios. I'm going to simply say, work the problem. Plug in the ratio you need. Do not give me all the ratios in the world. Do not sit down to step 1. Write out all the ratios. You'll be here forever. You get it? All right? In the book, that's what they take to each step. He makes you write out every one of them. If he has 29 reagents in there, you're going to write out 20, that many ratios. He's doing that for instructional purposes. But you know how to work the app. You only need to put in what you need to put in. And there we go. Worked out well, right number sig figs. Here's another one. Propane. How many moles of carbon dioxide can be produced when 2.25 moles of propane reacts? Okay, we're going to do that one. We're going to pause, and we're going to work it on the board. So let's take a look then at the answer here. Go 3 to 1, you run the numbers, and you get the answer. Okay, that's it. Over and over again. All right, to convert mass of a substance, well, we walked you through this, but you already know how to do that, right? What are you going to do when you have to convert the mass? What are you going to use? Dimensional analysis. You get it? And you're going to plug it in until the machine pushes it out. You get it? Don't try to remember. You can't memorize this. I'm going to say again, it's up to you if you memorize all this. But I'm not going to be testing you on what you memorize. I'm going to be looking to see whether or not you can run the process. Okay? So here it shows you how to do that. So we have an example here. So they want to know. If we start with that number of grams, they've already shown you here. So we're going to work it through here. 54 point, is the equation on here? Is that the same one?
No.
Okay, let's do this one then. All right, so let's do this problem here. Grams. So let's do it. You ready? We're going to pause and we're going to work the problem. Okay, so we have this problem. How many grams of CO2 can be produced when 54.6 grams of ethylene is burned? So we have the ethylene, and we look for carbon dioxide. We do what? We start with the given, carry it through the what? Dimensional analysis. Does everyone see how this went through? You just times line, mole, mole to mole, here gram per mole, and you get the carbon dioxide out. All right, so let's look at another example here. Let's do this one then. Did we do this one already? Okay, so we're good there. See if we have another example. Okay, no more examples. All right, let's go to limiting reagent. You're going to hear me say reagent because I grew up in the era when that's the term we use. The proper term now is reactant, not reagent. Okay? Got it? So if you hear me say reagent, that's translated to you as reactant. You got it? It's a hard habit to break. The limiting reactant. When you carry out a reaction, notice we have two things in here. These are the pounds of, like anybody ever run short when you're baking? Anybody plan to bake 50 cookies, right? And you find you don't have enough sugar for what? 25? No? Never happens? You guys plan too well.
Yeah.
Those are called your limiting reactants. When you run short, right? If you're short on sugar, right, you got to cut back on your batch, right? You get it? But you have limiting reactants. When it comes to limiting reactants, there's some species in there that you can only get as much out as that reactant you put in. So whichever one produces the least amount is the limiting reactant. To find that out, you have to run calculations on both species. Note that. To find a limiting reactant, you have to run calculations on both reactants. Okay? For example, I can go back. In this case, I would have to run calculations on heptane and on oxygen to determine which one is causing it to be limited. Does everyone follow the concept? You can only get out as much as the one that's causing it to be limited. If you're short on eggs, you have to cut your baking batch down. But obviously you guys have told me you're never short on eggs. So, bad example. Does everyone get that concept? When we say run calcs on both of them, how do we run our calcs? Dimensional analysis. You got it? Which means that if you have to do a limiting reactant problem, how many dimensional analysis you're going to have to do? Two. Make a note of that in your mind. If that problem says limiting reactant, you have to do this dimensional analysis twice. You have to do it on the first reactant, and you have to do it on the second reactant. Does everyone understand that? But is the process different? Nope. You say, why in the world would chemists sit around and think to make us do this over and over again? Because it's fun to us. Okay? So that's what limiting reactants are. It's the same thing we just showed you, but you're going to do it what? Twice. And you're going to know what? Reactant 1 and reactant 2, reactant A, reactant B, whatever you want to call them. And you're going to let the machine, and when you get to the end of the machine, you're going to look at the one that gives you the smallest value, and that's your answer. But you have to do it twice. So you have to be patient and do it twice. You can't get in and say, oh, this is close enough. You have to be patient and do it twice. Got it?
At least, right? If there's more.
But in your case, we've limited you. Remember the scope of the reaction we're doing? The top reaction you have, and there's a double displacement.
Okay.
Or redox, which is only 2 species. Okay. You get it? You're not getting a tertiary reaction. You're not going to see any of those in here. So you only have to do it twice. That's it.
And I thank you for that.
All right, here we go. So let's look at this carbon monoxide, right? Okay? Watch this now. Carbon monoxide and hydrogen are used to produce methanol. That's what they use to produce. The balanced equation is given. So we've already balanced it. You have to balance them now. You have to check them and make sure they're balanced. Once they're balanced, use the coefficients. Once they're balanced, that's it. Don't use any other calculation, any other counting. Okay? So if I want to do a dimension, so if I want to know limiting reactant, how many times do I have to run the machine? And you know how to run the machine now, right? You don't have to memorize it. You run it until you get to the final answer. So I'm going to run a dimension analysis on what in this case? Carbon monoxide and hydrogen. Does everyone follow? And when I get to the end of that dimension analysis, I'm going to look at the one that's the smallest, and I'm going to proclaim it as the limiting reactant. Does everyone follow how we do it? We're just going to do, as soon as you see limiting reactant, run two-dimensional analysis. The one that's the least is your answer. Okay? So let's do it on the board. I want to do. So here we have the example there of carbon monoxide and hydrogen are used to produce methanol. We have the balanced equation. We have 3 moles of carbon and 5 moles of hydrogen. And we are looking for the limiting reactant. If we look for the limiting reactant, we have to run a dimension analysis twice on both of the species. We run the dimension analysis first on carbon monoxide, and we get 3 moles of methanol as shown here. We've already worked through this offline. And now we work through here hydrogen, and we notice that there are fewer moles of methanol produced with hydrogen than there are with carbon monoxide. Therefore, hydrogen is the limiting reactant. Is what limits this reaction. Okay? So limiting reactant is a chemical reaction. It is a substance that runs out first. It stops the reaction. What's left is called the excess. So I could ask you, what's in excess? The answer to what's in excess is the one that's what? The largest. Does everyone follow that? Okay? You have the limiting and you have the excess. Most chemical processes do not run one-to-one. There's typically excess of one or the other reactants. Okay? And there's good reason for that. They have to drive it. And there are impurities, the whole kind of bit. And so they drive it so they can get the pounds out. So production tends to look at how many pounds I can get out. And so when I get the pounds out, I have to put a little bit more of this in it to drive it through because of impurities, hiccups, etc., etc. In this case, how many grams of carbon monoxide are formed? See it now? We ask how many are formed. In the example here, we're showing silicon dioxide and carbon. This is called carbon reduction. This is what Hemlock Semiconductor does down in Carrollton, Kentucky. They do this in an arc furnace, burn it, send the metal up here, then make metal convert that metal into your cell phones. This is what happens. This process, run like that. This is dug up on the north shore of the U.S. and southern border of Canada. A lot is dug there. Okay, it's a big trade there. So anyway, and you put this carbon is just trees, charcoal, coconut trees. There's a reason for it because they lower in sulfur and phosphorus. But anyway, so this is what happens. Run that. So if you make this, so what do I have to do to solve this problem? Run a what? Two machines. Run two-dimensional analysis. Right? To determine the limiting reactant. Is everyone with me? I'm talking too fast. We're okay? Okay. So here, we run the calcs. We do what? Here, gram to mole, mole to mole. Everyone see why I went mole to mole? Because I can do that. Does everyone see where I get the 2 from? Balanced equation. Don't have to do any calculation, run any number, just look at the values. Does everyone see where we get this from? This is molar mass. You calculate what? Carbon plus oxygen gives you that value. You get this out. And so these are grams. So here it took it all the way out to the grams, did it not? It didn't stop at the moles. Okay? And you can stop at the mole, you can stop at the grams. Just depending on where you have to go and what the problem asks for. We do the second time through with carbon. We do carbon the same way. This is gram per mole, so it's 12. Here, does everyone see where we get this? Carbon monoxide to carbon. We look back at the balanced equation. Carbon monoxide to carbon is 2 to 3. Okay? No calculation, no counting, just simply look at the coefficients. Run it through. So what's the limiting reactant in this case? What is the limiting reactant? It is it? So we get a 6 or something? 65, yep. So silicon dioxide is a limiting reactant in this case. And in fact, this is how it's run. Because this is cheap and that's not. So you run it until you deplete all of that. Okay? And this is reusable. Okay? And then we have what's called a theoretical yield. The theoretical yield is what you get when you simply look at the balanced equation and run the values through your machine, through the dimensional analysis. That is your theoretical yield. So now, in this particular case, of the reaction of silicon dioxide plus carbon, which reactor do I use to determine the theoretical yield? Do I use silicon dioxide or do I use carbon? I'm sorry? Right, that's the one you're using. Which is it? Silicon dioxide. Does everyone follow it? You get it? Because that's all you can get out. You can't get any more than a limiting reaction out. That's the concept. So if they ask for the theoretical yield, you have to run 2 machines through, right? And choose the one that's limiting, and that's the amount we should get out. So in this reaction, we should get out. How many grams should we get out of this reaction? This will tell me whether you got it.
65.3 grams.
That's it. That's how much I should get out. Why shouldn't I get this out? Because it's not a limiting reactant. You get it? I should only get this amount out. If I get less than that, you can almost guess how to do theoretical yield, can't you? The amount you got out divided by the amount you should have gotten times 100. Does everyone follow that? Okay? It's like basketball scores, right? He went 7 for 23. That's a bad night. You don't, okay? All right? You'll be on the bench. Okay? So here it is. It's the actual yield divided by the theoretical yield times 100. And we get the theoretical yield from what? The limiting reactant. If the problem doesn't give you a limiting reactant, the one that's in there is assumed to be the limiting reactant. But if you're given options, then you have to run the machine twice to determine it. If you're only given one reactant, then that's assumed to be the limiting reactant, which gives you the theoretical yield. And the actual yield is just how much we dug out. The way you determine the actual yield is simply what's given. There's no calculation to determine theoretical yield other than putting it on a balance, subtracting the numbers, and seeing what you got. So we'd have to tell you that I got. So for example, let's test you out here. Let's say if in this reaction you have silicon dioxide with carbon, if I got out 33 grams of carbon monoxide, what's my approximate theoretical yield?
Say that again, sorry.
I got out, in this reaction here, I got out 32 grams, 32 and a half grams. What's the approximate theoretical yield?
50%.
What is it?
50%.
50%. You're about 50%. You got about half. That's it. It's that straightforward. Do not complicate it any more than that. Everyone see where we got that half? I should have gotten 62. I got out 32, about 50%. You get it? That's it. That is theoretical yield. Okay. So on the space shuttle, lithium hydroxide is used to absorb carbon dioxide. And really want to do it because this is what they're breathing out. This is what they're exhaling. And after a while, you can poison it, right? Follow? Okay. So it's used to do this. This is a reaction. What is the percent yield of lithium? Yeah. Bicarbonate for the reaction of 50 grams of this give this number of grams here. Does everyone follow it? What is the percent yield for the reaction of 50 grams of this? Okay? And it gives that number of grams. Everyone follow it? What's the very first thing I need to do?
Dimensional analysis.
Dimensional analysis. Don't second guess it. What's my given for the dimensional analysis?
50.0 grams
That's it.
of lithium.
Yep. So you got to run that through your machine and see what you should get. Right? And you're going to compare that against what you got. Yeah.
Just so I'm assuming that they're assuming then that we know that the lithium hydroxide is the limiting reagent, because that's the only.
That's the only thing you have.
The only thing
You only work with what you have, and that's correct. Okay? You got it? In all reactions, we don't give you two to try to ask you that. This is it. Okay? All right? It is eliminated because actually they know that because you don't know how much CO2 is going to be breathed out and when you're going to run out.
Oh, sure.
You know how many pounds of this you loaded in there. You get it? This depends on breathing. Okay? This is going to be, you're going to have excess of this more time than not. But actually, I won't get into it. Okay. Okay, I was about to have a lot of fun. But, okay, here we go. So we have 50 grams, and we should run it through the machine. You know how to run it through the machine now, right? Okay. Calculate the theoretical yield. Everyone see why we ran it through this machine? And we see how we run it through. This is a slide on calculating percent yield. So we have the percent yield. We have the capacity to get what? 144, 142. Look, like we only needed what? That's pretty cool then. 50%. You get it? Do I need to beat this horse? Are we okay? Hang in there. Let's talk about energy. Any species that shows up in a balanced equation can be used as a conversion factor and is part of the overall balance, including when we express energy. Thus far, we have been showing you about the atoms, the compounds, and elements in there. There's also energy, and that energy can be in two forms. Exothermic, which means that's what happens when you blow up something. Boom, it comes out, it's released. Or endothermic is what happens when we create. It absorbs it. It's like photosynthesis is your classical endothermic. Photosynthesis is the chemistry of life. Okay? So, we either need to absorb energy or release energy. Get it? You can absorb or release energy. And we express that energy in kilojoules. That's the unit. That's the unit we express it in. We've already talked about these types of units. So we have what's called a heat of reaction. The heat of reaction is the products minus the reactants. When this value is negative, when the products minus reactant gives you a negative value, it's called exothermic. That value is written on the right side of the equation. You want to note that, okay? If this is negative, that means it's exothermic. So if it's exothermic and you report it, you must report it with a negative value. If you write it in the chemical equation, you must write it on the right side of the equation. Everybody with me? I'm summarizing this and we're going to show it to you. Okay? So delta H, that's the energy. Products minus reactants. If it's negative, it's exothermic. If it's positive, it's endothermic. If it's exothermic, you write the value on the right side of the equation. If it's endothermic, positive, you write it on the left side of the equation. You're going to see that. That's what this is pointing out. So if I look at this equation, is this an endothermic or an exothermic reaction? What is exo, right? You know it by two ways, right? It has a what? Negative value. And notice where's the energy written?
On the right side.
That's how you know. Straightforward. If I were doing calculations and I want to know how much energy came out of this reaction, do you think you could do it? That's supposed to be yes. Everybody say yes.
Yes.
There you go. Thank you for humoring me. The reason you think you can do it is because, what are you going to use to do it? Dimensional analysis. You get it? You're going to use dimensional analysis. And since this is in the balanced equation, what is the ratio of energy to HCl? Spit it out. Just try it.
185 to 2?
185 to 2. Why did you say that? Because that's what's in the equation. It is that straightforward. Does everyone see what she just did? The relationship of energy to HCl is 185 over 2. What is the relationship of energy to chlorine? 185 to 1. Because it's in the balanced equation. And if you need energy, you simply start doing the dimensional analysis until you need it, and you put it in that slot. If it asks you for energy out, you start with your given. Don't try to figure out, oh, I don't know anything about this energy. Do the steps. Run the machine. Okay, we are going to stay a bit longer and finish this one. Okay? So this is what an exothermic reaction looks like. It starts uphill and it falls off the cliff and it's cool.
So that was like that Sagal or whatever that we did in lab last week.
You got it. This is what's happening. Yep. Yep. Okay. So this is like giving off the energy here. It released the energy. You felt it. You felt the explosion. You felt the heat from it. You felt the energy from it in an exothermic reaction. So exothermic reaction falls off the cliff. It goes downhill. Okay? And we produce that much energy. The amount of energy is 185. The sign tells us that it's exothermic. So recall the magnitude is 185. The sign says it's exothermic. Endothermic, we just talked about already, haven't we? Where did we write this? You notice it's on this side of the equation? Now, when you write in the equation, it's always plus. You just put in the equation. Okay? When you report it independently, you write the sign. In the equation, you write it in the equation. It's just part of the reaction chemistry. It knows that it's plus and minus. On the left side or the right side. Takes a little bit to go uphill. We see more exothermic reactions than we see endothermic reactions. And here's the equation. The sign is positive, we've already told you that, or the sign is negative. So, tell me about this. Endothermic or exothermic?
Exothermic.
Endo or exo? Endo or exo? Even though you don't know what it is, right? You know that it is. Folks, you just survived chapter, what was this, 9?
Yeah.
All right. That's it for today.